Welcome back to PV Online. Today we're going to take a look at curved mirror calculations. And for this entire unit, there will be two equations that will be able to help us calculate everything that has to do with curved mirrors. Curved mirrors are more interesting because you can get different images depending on where you place the object. Okay, so you should have watched the video showing the ray diagrams of curved mirrors. Concave mirrors are interesting in that the image is different depending on where you place the object. So we've got a concave mirror. This is a huge, important information, the fact that you have a concave mirror. Whenever it's a concave mirror, that means its focal length is positive. So since I have a focal length of 15 centimeters, that is going to be a positive 15 centimeters. And you're going to find that the math in this unit's not hard. It's going to be paying attention to signs. All right, so we have an object that's 2 centimeters tall, so I'm going to call that the size of the object. Now, depending on what website you go to or what textbook, you might see different letters. It might say HO for the height of the object, but just remember it's the same thing. It's just going to be different letters. So the size of the object is 2 centimeters. And it says it's placed 20 centimeters in front of the mirror. That's going to be the object distance. Our distance is always going to be how far is the object from the mirror. So we have a 20 centimeter distance. And so the first question is, it says find the image position. So I want to find DI. What is the position of the image? So we're going to use the relationship that 1 over F equals 1 over the object distance plus 1 over the image distance. Now you have a separate little video that shows you how to use the calculator on this. That x to the minus 1 button is going to be hugely helpful to you. Since it's a concave mirror, that means my focal length is positive. It's just 1 over 15. My object distance is 20 centimeters. And so now I can calculate for DI. Okay, this is an online calculator, so it's not going to look exactly like yours, but it's still got the same functions. So if I'm going to throw this in my calculator, I'm going to take 15 and hit this. Now your button might say x to the minus 1, and all x to the minus 1 equals is 1 to the x. So I'm going to put that in there. So I want to take the 1 over 15 minus, I'm going to enter 20 and hit that x to the minus 1 button. When I do that, I get 0.016667. We just found what 1 over DI equals. So you need to remember to hit that 1 over x button once again. And when I do that, I get 60. So my image is going to be farther away from the mirror. Now for part B, the question is, find the size of the image. Well, this is going to be our second equation, and our second equation is going to be the size of the image divided by the size of the object equals the image distance divided by the object distance. It's just a ratio. What that means is the farther away your image is, the larger the image is going to be. So I'm looking for the size of the image. The size of the object we said was 2 centimeters equals the image distance, which we just calculated as 60, divided by the object distance, which we said was 20. That means the size of my image then is going to be 6 centimeters. So this would be also, we could call that the magnification. The magnification is simply the ratio of the image distance over the object distance. So you can see that if my object was 2 centimeters, my image is going to be 6 centimeters. It was magnified by a factor of 3. Let's look at example 2. Sally is applying her makeup while looking at a concave mirror. Now the thing that's interesting about a concave mirror, that's typically what you find in a bathroom. And that's going to be when you look in and all of a sudden your face is huge. Since it's a concave mirror, we know then that the focal length is positive, so that's going to be positive 22 centimeters. She looks at it from a distance of 15 centimeters. She's the object. That means she's 15 centimeters away from the the mirror. That's going to be the object distance. And for part A, we're simply asked to find what is her image distance. So using our mirror and lens equation plus 1 over DI, let's go ahead and plug in our values. So I have 1 over 22 equals 1 over the object distance, and the object was 15, plus 1 over DI. Let's solve for DI. And I'm going to start with the focal length. So my focal length was 22, so I'm going to hit 22, but I have to remember to hit that 1 over x. And I'm subtracting 1 over 15, so I need to make this minus 15, hit that 1 over x button. When you do that, I get negative 0.0212, but I've just found DI, so I have to hit 1 over x button again, and when I hit equal, I get negative 47.1 centimeters. And I get negative 47.1. Now this is where the signs become very important. If you ever have a negative image distance, that means it's a virtual image. And a virtual image is going to be one that you see inside the mirror. So when you're in front of that focal point, do you see the focal point is 22 centimeters, but the object is 15? You're now going to see that image inside the mirror. Let's look at our third example. We've got a concave mirror, a focal length 15. It's concave. That means that the focal length is going to be positive 15. And I have an object that's 2 centimeters tall, so the size of my object is 2 centimeters. And I'm placing it 15 centimeters in front of the mirror, so that means my object distance is 15 centimeters. And the question is, find the image position. So for part A, we're going to use our mirror equation, 1 over the focal length equals 1 over the object distance plus 1 over the image distance. So if I plug in 1 over 15 equals 1 over 15 plus 1 over di, look at what happens. If you take 1 over 15 minus 1 over 15, you're going to get 0. If you try to hit that x to the minus 1 button, it'll say undefined, or it'll say error. You'll have a domain error, error dividing by 0. And what that means is that there is no image distance because there's no image. So anytime you place an object at the focal point of a concave mirror, you won't have an image. It'll just be a nice big beam of light. And that's typically where they put the light bulb for a flashlight or a headlight. They'll place the light bulb at the focal point of that mirrored surface so you get this nice beam of light. Now for part B, it says determine the size of the image. Well, the size of the image, there is no image. So if there's no image, there's not going to be any size of the image. Okay, now we have an example where Wendy the witch is polishing her crystal ball. And the question is, what is the focal length of the crystal ball if she can see her reflection 4 centimeters behind the ball when she's a distance 15 centimeters in front? Notice the curved surface. All of a sudden, this is no longer a concave mirrored surface, but this is a convex mirrored surface. So if we take a look at this, we were given that the reflection is back here. The reflection is, the image is inside that surface. That means that my image distance is going to be a negative 4 centimeters. That is going to be a virtual image. Wendy is 15 centimeters in front, so my DO is going to be 15 centimeters positive. She's out here. Here's the curved surface. The image is inside. Now the question is, what is the focal length of this mirror? So using 1 over f equals 1 over the object distance plus 1 over the image distance. So our object distance is 15 centimeters. She's 15 centimeters. My DI is negative, so I'm just going to make this minus 1 over 4. I'm just pulling that negative sign out. And when I calculate this, let's see what we get. And all of a sudden, when I calculate this focal length, I get negative 5.45 centimeters. And that's actually very good because it's a convex mirror. And a convex mirror we call a negative mirror. That means its negative, or its focal point will always be negative. Convex mirrors produce virtual images every time. So anytime you calculate it, if you're doing a calculation and you're calculating the image distance, if your image distance doesn't become negative for a convex mirror, you've got a sign problem someplace. Okay, let's take a look at our final example. And this time we have a reflecting sphere that's sitting in the yard as a decoration. A bird's going to approach it and is 10 centimeters from the sphere. So we know that the distance from the bird to the mirrored surface is 10 centimeters. So the bird is the object, that's going to be 10. All right, if it's from a blue reflecting sphere, a focal length 12 centimeters. All right, now I want you to look at this. Do you see this curved relative to the bird? Is that a concave or is that a convex mirror? And that's a convex mirror. So since it's a convex mirror, we know that that is a negative focal point. It has a negative focal point. You are going to have to add that negative sign in doing any of your calculations. The question is find the position of the image. All right, we know all convex mirrors produce virtual images. That means your DI has to be negative or else we've done something wrong. So let's use our mirror equation. 1 over f equals 1 over the object distance plus 1 over the image distance. The focal length is negative 12. I'm going to throw that in here. Equals 1 over the object distance, which I said was 10, plus 1 over di. When I subtract the 1 over 10, no matter what that number is, when you have a negative something and you're adding another negative, it's always going to have a negative value. So when we solve for di, let's see what we get. Okay, let's do our last calculation. And this time we're starting out with a convex mirror. That means my focal length is negative. So I'm going to start out with a negative 12. So I've got a negative 12. I have to hit the 1 over x button minus the object distance, which was 10. So I have to remember to hit the 1 over x button again, and when I do that, I get negative 0.1833, but that is going to give me the 1 over di, so I have to hit the 1 over x button again, and when I do that, I get a negative 5.45. The image of the bird is going to be inside that sphere, and it would also be about half the size. It's going to be about half the size because if my object distance is 10 centimeters and my image distance is 5.45, remember the magnification is simply a ratio of those two, and 5.45 divided by 10 is 0.545. So this image is going to be a lot smaller. All right, we've done lots of examples. Feel free to look at these again, and we'll see you next time.